Hello, welcome to video 20 in the lecture Advanced Mathematic Modeling. So in the last videos I showed you examples of discrete distributions, and there we often came across this factorials for all kinds of discrete distributions. And when you now want to solve problems with these factorials, this sometimes tough mathematics, and today I want to show you a worked example, the famous birthday problem, where we learn how we can rewrite such factorials in analytic functions, so we have more powerful technique to address, to solve such problems. So, and this birthday problem is the following. So let's assume you have n people. So usually I say the people in the classroom, and n is 20, 30 or something. And then we ask, what is the chance that at least 2 persons have birthday at the same day of the year? This problem is famous because most people from intuition would rate this chance or this probability to be rather small, whereas in fact when we calculate it precisely, this probability is much higher than our intuition would usually say. And for the fun of it, so we play this game here on Earth, where the year has 365 days, and then we can play it on a different planet like Jupiter, where we have 1500 days in the year. Okay, so how do we address this problem? So first we might realize that this is this kind of problems where it's useful to use the complementary event. So we can say, we say Qn, that's the probability that all people, all persons, all of these n people have birthday at a different day. Yeah, and then it's clear that what we are looking for, the chance that at least 2 people have birthday on the same day, is 1 minus Qn. So that's just the complementary event. And this probability is more easy to calculate. So how do we calculate the probability that all people have birthday on a different day? So, and now and this probability depends on the number of people. So, and then it's clear, so that this Q, and sometimes when you don't know the solution directly, it's good to play around with parameters. So for example, if you have 366 persons in the room, then the chance that they all have birthday in a different day is 0, because at least then 2 need to have birthday on a different day. So you see, this should be a decaying function of n. And now we can see what would be Q of 1. So we have only 1 person, then the probability is 1. Now take 2 persons. So what's the probability that both have birthday on a different day? So that's the first has birthday on whatever day, and this for the second, then there is 364 days left, and we divide by the number of days. So that's the probability is Q for 2 people to have birthday on different days. Now we take Q3, and so it's again, so you see it's again a counting problem. So then for the first we choose 1 person, then for the second we have 364 days left, for the third we have 363 days left, and then we have to divide by 365 times 365 and so on. And then we can write down Qn is simply, so if we just continue this, 364 multiplied until we have 365 minus n plus 1, and we have to divide by this 365 to the power n minus 1, just following the sequence n number of times. And then maybe to make it more nice, we multiply here by 365 divided by 365, so that we have 365 to power n, and then we see we can write this as 365 faculty, so that's the product of these numbers going down. But then we have, if we write this faculty, we have too many terms, so then we have to divide by 365 minus n faculty, so that here in the denominator we just have the correct number of terms, and then we still have this 365 to power of n. Yeah? So this is just a counting problem, yeah? Discrete counting problem. And now if we want to have an arbitrary number of years, which we call k, and then we can say the probability Qn is k faculty divided by k minus n faculty by k to power n, and what we're really looking, this Pn equals 1 minus Qn. So, and then this discrete counting problem is solved, and we could think we are finished here. But there's two issues with this. The first is, with this solution we cannot really see something. Of course we cannot try to plug in numbers, plug in this k and plug in certain number for n, and then we can solve this in principle. But then the faculty is a function which is really fastly increasing, and when you take a normal calculator and you want to calculate 360 faculty, you will get error. So usually you have overflow. Now when you do this with MATLAB or something, MATLAB is doing tricks behind the scenes. So nowadays MATLAB, maybe not the first MATLAB version which emerged some time before. So internally this faculty is transformed into, this k is transformed to a floating number, and then there is some tricks. This faculty is transformed to a gamma function, and then from the gamma function of a floating argument there are some formulas, and MATLAB is doing something similar that we will do now also. But if you just have a simple calculator which just can multiply and divide numbers and so on, you cannot solve this because you have too many digits. Right? So in practice this is useless. This is also useless too, because if you want now to solve something. So, and here now is the technique I want to show you, or to introduce you. So we will apply Stirling's formula. And that's the useful formula if we have faculties. So if you have equations or terms with faculty, Stirling's formula. And this goes like this: if we have n faculty, we can approximate this by square root of 2 pi n times n over e. E is the Euler number, to the power of n. That's a really useful formula. So I made this in red to emphasize this. This is one of the formulas which is not bad to memorize. I mean, usually you don't have to memorize formulas, but this is not a... If you work more with this kind of problems, it's a cool formula. It's not exact, it's an approximation, but if this n faculty gets so large, the error that you do, you can neglect. And so here you see that the faculty increases as a weird function, n to power of n. That's a really weird, very fastly growing function. Okay, now let's see how we can use this formula, the Stirlings formula, to simplify what we have here. And so we have here 2 times the faculty, k to n, and so we have to apply 2 times the Stirlings formula. So if we do this, then we write down this qn. We have here, first take we take the square root terms. Since we have 2 faculties, this factor 2 pi there will cancel each other, and then we have from the faculty terms we have faculty k, square root of k, and square root of k minus 1, because here we have k faculty and k minus 1 faculty. So that was the square root term. So, and then we have k to power of k, then we have k minus n to power k minus n. This was this. Now we take the e factors, e to minus k. We need minus because this e here is in the denominator, and then e to minus k minus 1. Now we have done this the Stirlings formula for the faculty term, and then it's still this here missing, so we still need here times k to power of n. So we have now used the Stirlings formula. This looks maybe even more complicated than what we had before, but these are all now analytic functions that we can deal with. So now we have to sort terms, and so maybe we can rewrite this here as k over k minus n, and I rewrite the square root as 2 power 1 over 2. Then we have here k over k minus n to power k. Then we have here, it was this. No. And then we combine all these k terms. So let's write this first. Here I write k over k minus n to power minus n. And then you see like this, we have here this k minus n over k minus n. So we have here k minus n to k minus n to minus n. So with these 2 terms we have this. And then here we have k over to power k and k to minus n, this term. So we just have restructured all these k to n and k minus n, so that we always have the fraction k over k minus n to power something. And then we still miss the e functions. We can divide by e to minus k, and then we are left with e to minus n. Yeah. So it's restructured a little bit, and we start to see some order. And now we can put all this k over k minus n together. So we have k over k minus n, and we have to take this to power k minus n plus 1 over 2 times e to minus n. Yeah, and maybe I should recommend you, when you see now all these calculations, when I finished with this lecture, try to take an empty sheet of paper and try to do the calculation on your own, and only when you're stuck, look at the solution that I have. So that's a good exercise to train your analytic skills for manipulating formula. Okay, so what is our next strategy here? In principle, we could say, okay, now we have a nice formula, and now we can plug in numbers k and n and work this out here. Okay, but now I want to get more insight, some intuitive insight into the solution. And now we want to use the fact that typically n is much smaller than k. Yeah, because you saw already when n equals k, this gets trivial. So can we make an approximation for n is much smaller than a? So let's write this down. We are interested in approximation for n is smaller than k. So when we want to do this, it makes sense to rewrite this here, this fraction here, in a term that something is small. So if n is smaller than k, we don't see here a small factor or a small term in here, but we can rewrite this as 1 plus n over k minus n, and now the rest is the same, k minus n plus 1 over 2 times e to minus n. And so what we have done here, this fraction is now 1 plus something which is small. So, and now we have 1 plus something which is small, and this cries already that we can then use some Taylor expansion of this whole term around 1. But first, I mean, one trick we also do here, maybe I write this trick or somewhere there. So if you have x to power x, then we can write this as e to ln x times x. I mean, that's always the way how to write x to something x. Even if you want to take a derivative of this term, you first write it like this, and then you can take the derivative. And so here we have this also, we have something k over k minus n to power k minus n. So let's rewrite this so as e to ln this times this. So all this term that we had here, so this was just a remark to show you what we are interested in. So, but now we continue with our reformulation of this. So we rewrite this as the exponential of the logarithm of this here, 1 plus n over k minus n times e to ln x times x, exponential of ln this times here the exponent times k minus n plus 1 over 2. That's the exponential finished, and then we still have the term e to minus n. Yeah. So, and now we have here a logarithm of 1 plus a small number. So what we do now we can use Taylor exponential. The logarithm of 1 plus x is something like x minus x squared over 2. So expand this in a Taylor function, and we go to the second order. And here is something hidden. When we go to the second order, why do we need to go to the second order? And that's a very fundamental, actually very deep question, for which I don't have a cool answer. What you could do, for example, in the derivation, what I show you in the following, go only to the first order and you will see, you will not come to a correct result, and then you always go to next higher order until you find a result that you think is interesting. But this is something very deep here, because you need the same thing when you want to derive, or how, I don't want to say too much now. So when you want to derive the diffusion equation, and in principle there is a very similar trick, and you have to go to the second order, and that's something behind this, that in the diffusion equation you have the second derivative in space and only the first derivative in time. So all the phenomena of diffusion are related to the fact that in this Taylor expansion here you have to go to the second order term here. Okay, but just let's develop this in a Taylor series, and we go to the second order. So now how do we continue? Maybe first, in order to save us space to writing, so now if I always now I will work the terms here, and then always have to write exponential of something. To make everything simple, I now for the moment calculate log of q, and then this exponential goes away. So what we do now, so we look what is the log of q. So this exponential goes away, and then we have just the log here of this here, and this log we replace by this Taylor series, which means then we have the first term, that's just the x, n over k minus n, and then minus 1 over 2, and then this factor squared, n squared over k minus n squared. And this was, can you still see it? So this was for this log we have here this 1 plus x. So this term, we have this term minus this term squared over 2. And this is this here. And now we need still to multiply times k minus n plus 1 over 2. And then we had here the whole thing multiplied by e to minus n. And since we now take the logarithm of the whole thing, this means we just have to subtract n. Yeah. So we use the trick that we calculate log of everything so that we have less to write. So, and now we have here terms, and we can now try to factorize things. So, for example, first we have here this subtraction of things, so we take a factor n out of everything. So this is n times something. Okay, and now we have to see, you have now to factor this out, and for example you see when you have here this term k minus n, you divide by k minus n, this cancels, we take a factor out, and then we have here just 1 left. And then from we get from this here, we get minus n over 2 k minus n, because one n went out, 1 k minus n cancels with this here, and that's left. And then we have still to multiply with now we take this 1 over yeah, let me first write it down. 1 plus 1 over 2 times k minus n minus 1. And just if you multiply this out, you see that's the same. So we have written this a bit more simple, and now we multiply these two factors with the parentheses. So it's n times, and then we have 1. Then we have plus 1 over 2 k minus n minus n 2 k minus n minus n over 4 k minus n squared minus 1. And then you see first these terms 1 cancel, and now you could see, now we take the case that n is smaller than k minus n, that n is much smaller than k, and so k minus n is of order k. So then we have here term n over k, and here we have a term n over k squared. And then you see this term is much smaller than this, and we can neglect this term also. So that's, now we do an approximation when we leave this term out. And so that's the second approximation here. So the first approximation was that in this limit n is much smaller than k, we made the Taylor approximation of the log. Oh, sorry. We made this approximation, that was the first approximation, or the very first was the Stirling, which was an approximation. Then we made the logarithm, the approximation. Now we neglect the second order term here, and then this is now left as minus n times n minus 1 over 2 k minus n. And so you see we came a long way, but you see how we simplified the system. So this q was first written as this, with this factorials and whatever. Then we had terms like this, and now by magic, it's just pure magic, we ended up with such a simple term for log q. And then now we can write down our probability that we are interested, p, that was 1 minus q, and this here is log q, so q is e exponential to this here, to minus n times n minus 1 over 2 k minus n. Okay, and now we could, so that's already something. This now you can put in your calculator, and this will give you numbers. But for simplicity, let's write it like this. That's 1 minus e to minus n squared. If this n is not too small, this is just n squared. And we say k is much larger than n, then this is about k. And then we have here 2k, and that's our Pn. So So this last approximation was not really necessary to have a, but it helps us because this is a term, of course, we know that's just a Gaussian function. Yeah, so this is something we have some intuition about this here, so we know how this goes. And that's now the difference if you want to get an understanding of a solution or you just write down a term. So if we would have stopped somewhere here or somewhere before, we would have a term which we might put in the calculator. But now we have something which we can directly sketch without computer. So we can now make a sketch of our Pn. So that's n. We want to know Pn. So this is an exponential function which is between 0 and 1. So we have a solution which is bounded between 0 and 1, which of course should be like this because it's a probability. And so now we have here an inverted Gaussian. So Gaussian is a function which starts from 1 and decays, but we make here 1 minus the Gaussian. So 1 minus the Gaussian, we start with 0, and then we have here the typical Gaussian function. Normally the Gaussian is also plotted for negative numbers, but here this n is only positive. Oh, sorry. Yeah, so we have our Gaussian. And what's the standard deviation of the Gaussian? That's the typical width of a Gaussian. That is this here. And this width is, so the standard deviation is here in the square root of k. So the standard deviation goes with the square root of k. And so now let's say k equals 365. Then we have square root of k is about 19. This means if we have here an n of 19, then the probability that two people have birthday on the same day is already about 1/2. So this gives you the scale when this is going to 1. And so you see this for 20 people we have already one probability 1/2, and if we have 30-40 people we have nearly probability 100% that two persons have birthday on the same day. And we have now this solved already also for other. So take the Jupiter with k equals this 10,000, or that was the Jupiter, the number of years, and take the square root of this is about 102. So it means on Jupiter we would need 100 people to have probability about 1/2 that two persons have birthday on the same day. So this example, I mean, of course this is not a big example. I mean, that's not really important for applied things in the world, like when you have two persons birthday on the same day. But it's a very nice example to learn all the techniques. First, nice example to counting. Typically this stops here. People are not interested anymore, but then we can use the Stirling. We learn how to work with these rewritings of terms. Then this cool thing, how to look for a small term so that we can make some Taylor things. If we have an idea what is small, and that's very often the trick. If you have an example, very often some quantity is much smaller than the other, then we can use some Taylor tricks. And the other trick is, instead of following q, we now solve for log q, which makes things more easy. Then sometimes one needs to have an idea that we can say, oh, we can neglect such a thing because yeah, it's much smaller than something else, and suddenly we are we see something, and then for graphic, to graph this, you have then just to see, oh, that's nearly a Gaussian, and then we can directly plot this. Yeah? And so suddenly we have some intuitive idea about our P of n. Okay, that was just an exercise. That was not for the development of theory, but I think it's a lot of cool exercises, so a lot of cool techniques which come again and again in this kind of calculations. So that's why I inserted this exercise here. So for yes, thank you for yet.